assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
We know that the spring constant k is going to be equal to 4 pi squared times m sub 1 divided by t squared. This is going to be equal to 4 pi squared multiplied by the mass 1, 4.00 kilograms, and then divided by the period. We know that the period is 20 milliseconds, so 20 times 10 to the negative third seconds quantity squared. This is giving us 1.97 times 10 to the fifth newtons per meter. We can essentially, we first need to determine where in its simple harmonic motion block 2 when the impact occurs in its simple harmonic motion. We can say that we know the frequency, the angular frequency is equaling 2 pi divided by the period t. And so we can say that the given value in the collision is 1/4 of the period. So we can then say that omega t is equaling pi over 2. And the location then of blue, we can say location of block 2 would be x. This is going to be equal to the maximum displacement times cosine of omega t plus the phase constant phi. We know that phi here in this case is equaling pi over. This gives us that x is equaling x sub m, maximum displacement times cosine of pi over 2 plus pi over 2. And this is equaling pi over 2 plus pi over 2 is equal pi. Cosine of pi is negative 1. So negative 1 times the maximum displacement is going to be equal to negative x sub m, negative maximum displacement. So essentially, this means that block 2 is at its turning point, given that it is at the negative maximum displacement when the impact occurs. So this also means that the string is stretched to an amount of 1 centimeter at this moment. So we can say that at this moment, string is stretched an amount equaling 0.01 meter or 1 centimeter. So we can then say that to calculate its after collision speed, we're going to use momentum conservation. So at this point, we can say that v, the final speed after the collision, is going to be equal to 4.0 kilograms. This would be multiplied by 6.0 meters per second. And this would be divided by 6.0 kilograms. So essentially just conservation of momentum. This is equaling 4.0 meters per second. So at the end of the impact itself, while block 1 is still at the same position as before the impact, the system now has a total kinetic energy. Now we're going to be using that the mass is equaling 6.0 kilograms, the total mass, and the kinetic energy would then be equal to 1/2 times this mass, 6.00 kilograms, multiplied by v squared, so 4.0 meters per second, quantity squared. This is equaling 48 joules. The potential energy at this point, U, would be equal to 1/2 kx squared. And this would be equal to 1/2 times the string constant that we had calculated in the very beginning, 1.97 times 10 to the fifth newtons per meter. And then this would be multiplied by 0.010 meters quantity squared. this is approximately equal to 10 joules. So this means that the total mechanical energy, we can say energy total mechanical would be equal to 48 plus 10, so 58 joules. And the system then reaches its new turning point. We're going to say that there's a new amplitude, capital X sub m, and this must be equal to its maximum potential energy at the new turning point, because at the turning point, there is no kinetic energy. Of course, there is only potential energy. So we can say then that the total energy would be equal, at its turning point, 1/2 k capital X sub m squared. And so the new maximum displacement, or the new amplitude, would be equal to square root of 2 times the total amount of energy divided by k, the spring constant. And now we can solve. 2 times 58 joules, and then this would be divided by 1.97 times 10 to the 5th newtons per meter. And this is giving us 0.024 meters. This would be the new amplitude after the collision and our final answer. That is the end of the solution. Thank you for watching.